आवाज आ रही सर मेरी? संजीव बोल रहा हूँ सर।
हाँ, आपकी आ रही आवाज, लेकिन ये पूरी
हाँ
सर अपना स्क्रीन खुला छोड़ गए।
हाँ, वही लग रहा है सर। मैंने अभी उनको बोला था, वो सुन ही नहीं रहे। मैंने कई बार उनको आवाज दी, उन्होंने
चलो
शायद
कोई,
ऑफ कर रखा माइक अपना।
हाँ हाँ, मैंने फोन किया तो फोन नहीं उठा रहे।
ठीक है सर।
चलो ठीक है, गाइस यू कैन सी माय स्क्रीन ना?
Yes.
Okay. Okay, so we will take this topic today, sextant का. कैसे स्टार्ट करें? एक मिनट होल्ड कीजिए. ओके, सो ये है आपका स्क्रीन, मरीन सेक्सटेंट. दिस इज व्हाट योर सेक्सटेंट लुक्स लाइक. और मरीन सेक्सटेंट में ये जो आपका दिख रहा है, जो मैं रेड से दिखा रहा हूँ, ये आपका फ्रेम होता है सेक्सटेंट का. ठीक है, ग्रेजुएशन सब इस पर मार्क्ड होती है. इस फ्रेम पे जो है आपका, उसमें आपका ये है इंडेक्स मिरर, होराइजन ग्लासेस है, शेड ग्लासेस फॉर इंडेक्स मिरर, होराइजन मिरर है, शेड ग्लासेस फॉर होराइजन मिरर. ये इसमें अटैच्ड रहते हैं. देन यू हैव दिस टेलीस्कोप विच इज ऑल्सो अटैच्ड टू द फ्रेम ऑफ द सेक्सटेंट. ये आपका आर्म है, स्लाइडिंग आर्म, ये यहाँ पे पिवटेड रहता है. Then you have a micrometer drum and you have a clamp here. So this is, देखा होगा आप लोगों को सेक्शन. और उसके पीछे ये जो ब्लैक दिख रहा है आपको यहाँ पे पीछे, ये आपका हैंडल है सेक्सटेंट का. नाउ ये चीजें जो हैं, दे आर ऑल फिक्स्ड टू द सेक्सटेंट. जब हम सेक्सटेंट को जीरो में रखते हैं, ठीक है, सेक्सटेंट को हमने किस पर रख रखा है? जीरो में रख रखा है. तो ये जो इंडेक्स मिरर है और ये जो होराइजन मिरर है, दे शुड बी पैरेलल टू ईच अदर. ऐसे पैरेलल होते हैं. कहाँ गया? ठीक है, सो बोथ द मिरर्स शुड बी पैरेलल टू ईच अदर. अगर पैरेलल नहीं है, थोड़े से टेढ़े हैं, तो आपकी एरर आ जाएगी. ओके, सो सेक्सटेंट हम इसको बोलते हैं बिकॉज दिस सेक्सटेंट इज रिप्रेजेंटिंग 1/6 ऑफ द आर्क. ये जो आर्क है, ये 1/6 ऑफ अ सर्कल है, मतलब 60 डिग्री चाहिए. बट यू नो कि ये एंगल तो यहाँ 60 डिग्रीज है, बट यहाँ पे वी कैन मेजर अप टू 120 130 डिग्रीज. ये बिकॉज जो प्रिंसिपल है सेक्सटेंट का, उसकी वजह से. राइट, प्रिंसिपल क्या होता है वो बाद में देखेंगे हम. सो इट्स एन इंस्ट्रूमेंट विच इज यूज्ड टू मेजर द angle between two visible objects. It could be your horizon and star. It could be two stars visible. It could be what you call two terrestrial objects. It could be two lighthouses. उनके बीच में एंगल लेने का. ठीक है, यूजुअली हम लोग स्टार्स लेते हैं, सन लेते हैं. एंड वंस यू हैव टेकन द एंगल यूजिंग Norris tables and almanac, टाइम आपको मालूम है, dr आपको मालूम है, you can calculate a position line on the chart or you can calculate a fix अगर आप stars ले रहे हैं तो. ठीक है, so this is called taking the site. सेक्सटेंट का स्केल जो है 1/6 है. वैसे और भी होते हैं, सेक्सटेंट बोलते हैं हम लोग क्योंकि 1/6 है 60 डिग्रीज. वैसे क्विंटेंट होता है, क्वाड्रेंट होता है, ऑक्टेंट होता है. स्केल्स उनके अलग होते हैं, किसी के छोटे स्केल्स होते हैं, किसी के बड़े स्केल्स होते हैं. बट ऑन द शिप 60 सेक्सटेंट. प्रिंसिपल क्या है? प्रिंसिपल इज दैट व्हेन द सेक्सटेंट, when a ray of light is reflected from two mirrors, दो मिरर्स है, एक होराइजन मिरर है, एक इंडेक्स मिरर है, राइट, इन सक्सेशन in the same plane, then the angle between the incident and the reflected ray is 2 times the angle between the mirrors. ठीक है, ये मेरे को आपको एक वीडियो दिखाऊंगा, उसमें देखेंगे आप. The steps, अब ये नेक्स्ट, ये तो प्रिंसिपल आ गया आपका. अब एरर्स ऑफ द सेक्सटेंट. एरर्स एंड एडजस्टमेंट्स या करेक्शंस दो अलग अलग चीज है। हर एक इक्विपमेंट की कोई ना कोई एरर्स होती है और उन एरर्स को हम लोग करेक्ट कर सकते हैं, एलिमिनेट कर सकते हैं, ठीक है। और अगर एलिमिनेट नहीं कर पाए तो हम उसको एडजस्ट करते हैं, अलाउ करते हैं उसके लिए। सो एरर्स जो है इक्विपमेंट की होती है। तो ये आपकी पहली है, एरर ऑफ परपेंडिकुलरिटी। ये कब होती है? जब आपका इंडेक्स मिरर इज नॉट परपेंडिकुलर टू द फ्रेम ऑफ द सेक्सटेंट। सो ये आपका सेक्सटेंट का अगर फ्रेम है और ये आपका इंडेक्स मिरर है, अगर ये एग्जैक्टली 90 डिग्री नहीं है तो तब आपकी ये परपेंडिकुलरिटी एरर आती है। कैसे आएगी? अगर ये थोड़ा सा इधर को झुका है तो एरर आ जाएगी, या ये थोड़ा सा पीछे को झुका है, ऐसे एग्जैक्टली पैरेलल नहीं है, परपेंडिकुलर नहीं है, तो एरर आ जाएगी। जैसे आपने बचपन में करते होंगे ना, एक कांच का टुकड़ा मिला कांच के टुकड़े से क्या करते थे हम? सन की रे आती थी, सन की रे को हम दीवार में मारते थे, राइट, या किसी की आंख पे लगाते थे, और वो मिरर को ऊपर नीचे हम लोग घुमाएंगे तो सन का जो रिफ्लेक्शन होता है वो भी घूमता था, इज़न्ट इट? क्योंकि एंगल बदल दिया तो उसका रिफ्लेक्शन भी बदल जाता है। वैसे ही यहाँ पे है, अगर आपका ये परपेंडिकुलरिटी एरर अगर एग्जैक्टली परपेंडिकुलर नहीं है तो तुम्हारी ये परपेंडिकुलरिटी एरर आएगी। अब कैसे पता चलेगा कि आपके उस पर परपेंडिकुलरिटी एरर है? तो व्हाट वी डू इज वी प्लेस द आर्म एंगल एट 60 डिग्री, सेक्सटेंट को 60 डिग्रीज पर रखते हैं, एंड होल्ड द सेक्सटेंट हॉरिजॉन्टली, सामने से आपके सामने हॉरिजॉन्टल होल्ड करो, विद द आर्क अवे फ्रॉम यू। नॉर्मली कैसे करते हैं? जब हम पढ़ते हैं सेक्सटेंट को तो हमारा सेक्सटेंट ये होता है, यहाँ पे इंडेक्स मिरर होता है, यहाँ पे हमारा वो होता है, और ये यहाँ पे हमारा रीडिंग है, ये आर्क है। सो दिस इज फेसिंग मी, मेरी तरफ फेस कर रहा है, ऐसे ही तो पढ़ते हैं हम लोग। अब मैंने क्या किया, मैंने ये मेरा कौन सा मिरर है? इंडेक्स मिरर है ये। मैंने क्या किया, इसको घुमा दिया, आर्क को इधर ले आया, आर्क को इधर ले आया, तो अब यहाँ पे तुम्हारा इंडेक्स मिरर आ गया और ये तुम्हारा होराइजन ग्लास आ गया। और मैंने कैसे होल्ड कर रखा है सेक्सटेंट को? हॉरिजॉन्टली, एक सामने से, आर्क अवे फ्रॉम मी, आई एम स्टैंडिंग हियर, ठीक है, मैं यहाँ पे खड़ा हूँ, ठीक है, फेस मेरा यहाँ पे है, और ये मैंने इधर इसको मूव कर दिया, आर्क अवे फ्रॉम मी, एंड नाउ आई एम लुकिंग इनटू दिस मिरर, इंडेक्स मिरर में देख रहा हूँ। जब मैं इंडेक्स मिरर में देखूंगा, राइट, तो ये आर्क है और ये इंडेक्स मिरर है, राइट। तो आई एम पुटिंग द इंडेक्स मिरर यहां पे डाल रहा हूं मैं। तो मुझे ये आर्क एक लाइन में दिखा देना चाहिए, ये जो आर्क है ये वाला, उसका रिफ्लेक्शन ये है, ये सब एक लाइन में दिखना चाहिए। अगर एक लाइन में दिख रहा है मतलब मुझे ऐसे दिखाई दे रहा है, ऑल इन अ स्ट्रेट लाइन, ये ग्रीन लाइन, ये सब एक लाइन में दिखा दे रहा है, तो देन देयर इज नो परपेंडिकुलरिटी एरर। लेकिन अगर ये एक
आपकी आवाज ब्रेक हो रही है।
अगर जाता है ये आर, ओके जी, एक मिनट होल्ड कीजिए। अभी ब्रेक हो रही?
हाँ सर, अभी भी हल्की हल्की
ऐसा ब्रेक हो रही है।
ब्रेक हो रही है
एक
सर।
मिनट। ओके जी, ब्रेक हो रही है तो अभी इसको जोड़ देते हैं। 2 मिनट दीजिए, नेटवर्क चेंज कर लें अपना। ओके, मैं 1 मिनट को वापस आ रहा हूँ नेटवर्क से, इस नेटवर्क से हट के। हाँ जी, अब कैसी है? हेलो गाइस।
हाँ सर अब ठीक है।
हाँ सर, अभी आ गई।
सभी ठीक है सर।
ओके ओके, मैं किस में था? इस पर तो नहीं था।
सर अगेन स्टार्टेड।
सर फिर अटक रही है सर आवाज।
हाँ जी, स्लाइड
बीच
अटक
में
गई।
अटकने लगी थी।
सर अभी अटकी थी, अब ठीक हो गई है वापस।
ओके, स्क्रीन दिखाई दे रहा है?
यस सर।
ओके, एक काम करते हैं, आज मैं इसको यहीं पे छोड़ता हूँ। मैं आपको कुछ और दिखा देता हूँ अभी, विच विल बी इजी टू फॉर यू टू अंडरस्टैंड। इस टॉपिक को हम नेक्स्ट टाइम ले लेंगे। बहुत टाइम है आपके साथ, तो आई एम गोइंग टू शो यू सम वीडियोस। पहले इसको देख लेते हैं, इससे फिर आपका व्हाट आई हैव सीन इसकी अंडरस्टैंडिंग बहुत क्लियर हो जाती है और नेक्स्ट टाइम आपको समझने में इजी रहेगी। सो मैं आपको ये 20-25 मिनट के वीडियो हैं, 3 वीडियो हैं, तो शायद 5-5, 6-6 मिनट के होते हैं। मैं वो दिखाता हूँ आपको। Okay, so I'll share the first one with you. नॉर्मली ये वीडियोस मैं लास्ट में दिखाता हूँ, बट अभी देख लेते हैं क्योंकि आधे घंटे में ये टॉपिक कर नहीं पाऊंगा मैं। स्क्रीन दिखाई दे रहा है आप लोग को?
यस सर।
यस सर।
Everyone can see the screen?
Yes, sir.
यस सर।
Yes, sir.
भाई लोगों, मेरी आवाज आ रही नहीं आ रही है?
अरे सर।
यस सर, आ
Yes, sir,
रही
दिख
स्क्रीन
रहा
में
है
दिख रहा है सर।
हाँ सॉरी, आवाज आ रही है ना?
सर जी
यस
सर।
सर, आ रही है सर।
ओके ओके, ठीक है ठीक है। और स्क्रीन दिखाई दे रहा है?
हाँ सर।
यस
Yes,
सर,
sir.
स्क्रीन भी दिख रहा है सर, स्क्रीन विजुअल।
यस सर।
दिख रहा है ना? चलो
जी
फिर
सर।
चालू कर रहा हूँ मैं।
The sextant, probably one of the most recognisable pieces of navigational equipment. Safe to say you can't honestly call yourself a navigator until you've actually mastered it. Luckily it's a lot simpler than it looks, so we'll take a look at it together. We're going to have to break it down into 3 tutorials. This video we're going to look at parts of a sextant, the operational principles, and just generally how it works. Next time we're going to look into sources of error and methods for correcting them. And then the final video we're going to cover actually taking a sight with it. I would advise watching all the way through, as understanding the principles will really help when you're using it in anger. So let's start off looking at the parts of the sextant. The foundation of the instrument is its frame. The frame can be made of metal or plastic and just acts to hold everything together. It's important for the frame to be solid as it allows the instrument to be as precise as possible. Generally, a metal sextant will maintain accuracy better than a plastic one, and that's just down to the rigidity of the frame. But the big advantage of a plastic one is that it's cheaper. It's the shape of the frame that gives the sextant its name. It covers about 1/6 of a circle, or 60 degrees, with the Latin being sextans. At the bottom of the frame you've got the scale. Notice how the scale runs from 0 to 120 degrees, even though the sextant itself only covers 60 degrees. This is because of the double reflection principle, which the sextant employs to take its measurements. We're going to come on to that shortly. Attached to the frame is the index arm, and the index arm is the main moving part of the sextant, and you use it to actually take your measurements. At the lower end of the arm, you can see that it lines up with the scale, so you can read off your actual measurement. At the bottom of the index arm is a vernier scale and a micrometer drum. These are used along with the main scale to get a very precise measurement. The sextant should be able to measure angles to within 0.1 minutes with the vernier scale. Next to the vernier scale is a clamp, and the clamp is used to release that scale so that the index arm can move freely. You'll need to release the scale using the clamp when you're wanting to take a sight, but we're going to cover that in the third video when we're looking at taking sights. The mirror that's attached to the index arm is the index mirror. It's attached rigidly to the arm so that it moves as the arm rotates. And the scale that we looked at is related to the angle that you use the index arm and consequently this index mirror. The second mirror is the horizon mirror, and it's attached rigidly to the frame. You can see that this mirror is part mirror and part see-through. This is because you need to be able to see both the horizon straight ahead and the reflection of the celestial body that you're trying to measure. And this will become clear again in video 3 when we're actually taking measurements. Some sextants will have a semi-silvered mirror instead, and this makes this sextant a little easier to use, but it increases the cost. Opposite the horizon mirror you have the telescope. The telescope lines up with the horizon mirror so that you can see down the sights and see straight through it. Notice the angle that the horizon mirror is mounted at. It means that when you're looking down the telescope, the reflection in the horizon mirror is the index mirror. Finally, in front of each mirror you've got a set of shades, and you need to use these when taking sights, particularly sights of the sun, so that you can protect your eyes. If you don't use the shade, you can actually burn your eyes, and this is why so many old sailors would wear an eye patch. So we've assembled the sextant, but how does it actually work? This is where the sextant principle comes in. When the sextant is set at 0, looking straight at the horizon, you can see that both mirrors are looking at the exact same spot. The image in both parts of the horizon mirror should be identical. When you start to rotate the index arm, the image in the reflected part of the horizon mirror changes. The angle along the scale corresponds with the angle between the objects that you're looking at. You see how the scale will measure all the way to 120, not just the 60 degrees that the frame covers. And this is the sextant's unique selling point, its operational principle. The sextant works on the scientific principle of double reflection. With basic reflection, the angle of incidence, I, equals the angle of reflection, R. The angle of incidence is the angle between the normal, which is the line perpendicular to the plane of the mirror, and the incoming ray of light. The angle of reflection is the same but for the reflected ray. When you introduce a second mirror parallel to the first, you can see the ray of light continues with all the same angles I and R. Due to the law of reflection, we know that I and R are both equal, so we can actually just call them I to keep things simple. But as soon as that second mirror is no longer parallel to the first, an interesting effect occurs. Let's rotate our second mirror now by an angle, which we're going to call X. The ray of light still interacts with the original mirror in the same way, but now when it hits the second mirror, the angle of incidence has changed. It's now I plus X, and then due to the law of reflection, the angle of incidence equaling the angle of reflection, the angle of reflection here equals I plus X as well. If we look solely at the second mirror, the total deflection of the ray of light is I plus X plus I plus x, and rearranging this gives I plus I plus 2x. Compared to the first mirror, the difference is 2x. Overall, the reflected ray has been deflected by twice as much as the angle between the mirrors. This is the sextant principle. When a ray of light is reflected by two mirrors in succession, the angle between the incoming and outgoing ray of light is twice the angle between the mirrors. Now that we understand the principle, we can head back to the sextant and see it properly in action. We've already said that when set at 0 degrees, both rays of light come from the same direction. If we change the angle between the mirrors, say we rotate the index arm by 20 degrees, the rays of light now come from different directions. Although the angle between the mirrors is only 20 degrees, the angle between the rays of light is 40 degrees. This is that double reflection principle in action. The scale at the bottom has been calibrated to give the angle between the rays of light, not the direct angle of rotation of the index arm. This is why the scale reads all the way to 120 degrees across just 60 degrees of index arm rotation. Just look at that angle that the sextant can measure at its extreme setting. This is the sextant's huge advantage over the instruments that came before it. So, now we understand all the principles. In the next video we can look at the sources of error and how to correct them, before we move on to taking an accurate reading.
So this was
The sextant, probably one of the most recognizable pieces of navigational equipment.
सो ये पहला वाला देख लिया आप लोगों ने?
Yes, sir.
Yes, sir.
ओके, ये दूसरा वाला भी दिख रहा है आपको अभी?
If you watch the first video, you'll already know the principles
दिखाई दे रहा है ना? ओके, चलिए ये सेकंड पार्ट है अब,
behind the sextant
इसमें एरर्स ऑफ द इक्विपमेंट देख रहे हैं, एरर्स एंड करेक्शंस.
and be able to label all the different parts. If you haven't already seen it, I'd advise going back and watching it first. This video we're going to move on and examine errors of a sextant and methods of correction. There are actually many different errors possible on a sextant. We can split them into two different groups, correctable and non-correctable. One error, collimation, actually used to be correctable, but on modern sextants it's more usual for it to be non-correctable nowadays. Let's start by looking at the non-correctable errors. We'll just go through quickly as you can't correct for them anyway. Centering error, this is when the pivot point of the index arm is not perfectly aligned with the centre of the instrument. Prismatic error is when the two planes of the mirrors or glass planes are not parallel to each other. Shade error is the same thing, but it's for the shades, and it causes a slight deflection in the ray of light as it passes through the glass pane. Graduation error is to do with inaccuracies in the graduations of the scale, the vernier, or the micrometer drum. Worm and rack is effectively the wearing of the cogs that control the fine movement of the index arm. And collimation error, this is that one that was correctable on older sextants. It's caused when the axis of the telescope is not perfectly perpendicular to the plane of the instrument. Nowadays the telescope is normally rigidly fixed to the frame, so it's not actually possible to correct. And finally we've got instrument error. This is actually just a total of all the non-correctable errors that we've already discussed. It gives the user an easy way to apply all those manufacturing errors to their readings. Sextants come with a calibration card which gives this instrument error. In theory, the error should be negligible, but you can see from this example card that as the sextant reaches its extreme setting, you do need to take account of the instrument error. Now we can move on to the correctable errors. For the correctable errors, you need to correct them in the right order. First, you've got the error of perpendicularity. This describes the error caused when the index mirror is not perpendicular to the plane of the instrument. To check for perpendicularity error, you set the index arm part way, say 30-40 degrees, and then you look straight across the plane of the instrument so that you can see the arc both directly and reflected in the index mirror. You're looking for the real and reflected arcs to appear continuous and flat. As you can see, this mirror is set perfectly, and that's just because it's a computer-generated model. As I introduce some perpendicularity error, you can see the change in the view. the arc no longer appears continuous. There's a visible step between the two. To correct this error, you just use the adjustment screw. One useful tip for the adjustment screws and my method of correction is that you'll always be adjusting the screw that is at the top of the mirror in relation to the way you are holding the sextant. As you have to hold the sextant on its side to see this error, the screw on the side of the index mirror appears on top, so that's the one that you adjust. All you need to do is turn it one way or the other until the real and reflected views of the arc appear in a straight line. Once they do, you know that the index mirror is perpendicular to the plane of the instrument and is correct. Next, we're going to move on to side error. This is similar to the last error that we looked at, but it's for the horizon mirror instead. So side error is when the horizon mirror is not perpendicular to the plane of the instrument. You can spot side error when the instrument is set at 0 and you look at an object in the distance. If the real object and the reflected object are separated, side error is present. You'll notice the correction screws on the horizon mirror are not the same as those on the index mirror. The screws on the horizon mirror actually correct for both side error and index error. We're going to need to correct for both at the same time. So, what's index error then? Index error is when the index mirror and the horizon mirror are not parallel to each other when the instrument is set at 0. If you set the instrument to 0 and look through the telescope at the horizon, you can spot any index error. If there's a step in the horizon, index error is present. This is why index error and side error need to be corrected together. If you have a sextant with both errors present, images in the telescope will be displaced both horizontally and vertically. The horizontal displacement is due to the side error, and the vertical displacement is due to the index error. Now, everyone has their own way of correcting for these. For me, the simplest way is to just use the horizon. My reasoning is that for almost all sites, you're going to need the horizon anyway, so it should be visible, and it's obvious and easy to find. So, I start by setting the instrument to 0. I want everything to be lined up perfectly when the instrument is set at 0. Then, you can just look down the telescope straight at the horizon. You remember we already did this to check for index error. It doesn't really matter at this point if index error is present or not, because as we adjust for side error, we're going to change the index error anyway. At this angle, you can't tell about side error, because it's not possible to tell if there is a horizontal displacement. You could rotate the sextant by 90 degrees, which would effectively give you a vertical line to tell you about side error, but that's not actually necessary. All you need to do is to tilt your head slightly, and any side error will show itself with the real and reflected horizons moving apart. Obviously, if you've got a lot of index error to start with, it's harder, so you may have to tilt your head over to 90 degrees, so that all of the error that's visible is side error and none of it is index error. Normally, a 45-degree head tilt will be plenty. From this position, you just adjust the screw that is furthest from the frame. I tilt my head to the right, so this screw is now on top. Just turn it one way or the other until the horizon forms a continuous line again. As you bring the sextant back to its normal angle, the horizons may separate again. If they do, this is now due to the index error. Again, you adjust the screw that is on the top. This time it is the one that is nearest the frame. Turn one way or the other until the horizon is again continuous. Then you return to your tilted head position to check whether you've introduced more side error. If so, you can correct for that again. Now you repeat this process a few times until you've eliminated both side error and index error. You may get to a point where you can't eliminate both. If you find that you're just going back and forth between the two positions, you've taken out as much error as it's possible to remove. From here, just make sure your side error is eliminated. Then, any residual index error will have to be removed mathematically. You effectively measure that final little bit of index error by using the micrometer drum to make the horizon continuous. Then, any measurements you take will need to have that index error applied to them. If the error is measured on the arc, you label it on the arc, and it needs to be subtracted from all the measurements to make them true. Likewise, if the error is off the arc, you label it such, and it needs to be added to all measurements to make them true. So theoretically, you've now got a sextant with all errors eliminated and are ready to start taking sights. In the next video, I'm going to show you how. How do you actually use a sextant to take sights? In this video, I'm going to show you how you can use it to measure the altitude of a celestial body. You will need a properly adjusted sextant, so if you haven't watched the previous video about errors and corrections, I would recommend watching that first, and it's on the card at the top of the screen. What we're going to do is measure the altitude of this red body. I've just coloured it red to make it easier to see the technique that we're going to use. The altitude is just the angular distance between the body and the horizon, as measured from the observer's position. In this case, the sextant is the observer. So, the first step is to set the index arm and micrometer drum to 0, or as close to 0 as possible. If you have a small index error, of course, 0 on the scale will not quite be 0 according to the instrument. At this point it doesn't really matter because you're going to apply index error at the end. While set at 0, the instrument is basically just a telescope. You can look through the sights and see an image. As the instrument is like a telescope, you will obviously need protection when looking at bright objects. This mainly applies when you look at the sun, but do be careful if you're looking at anything really, because they can be surprisingly bright. You can use these shades as eye protection. There are set in front of each mirror, named accordingly, so you've got the horizon shades and the index shades. You will need to use both for proper protection. If I aim straight at our body and apply one of the index shades, you can see half of the image is suitably dimmed. If we now swap over and apply a horizon shade instead, you can now see the other half of the image is dimmed. Applying both a horizon shade and an index shade gives you full protection. It's safest to start with all of the shades across, and then you gradually remove them until you can see a clear image. With experience, you'll gradually learn the best combination for different situations. If the body is dim enough, you may not need any shades, and I'm actually going to remove them all for this example, just to help with the clarity of the explanation in the video. So, for the sight, you start by looking straight at the celestial body, with shades adjusted as necessary. With the sun, it's easy, but with stars, they may take a little bit of finding. You will want the body aligned right in the middle of the image, half of it reflected and half of it true. But here is one of my little tricks. While you continue setting up the sight, actually get the image in the middle of the horizon mirror instead. It will make it way easier to stay focused, especially on a small star or something hard to see. We'll align it properly when it comes to the fine adjustment at the end. Next, you want to get hold of the clamp at the bottom of the index arm. This will allow you to move the index arm freely. Have a little practice wiggle just to see how the image in the horizon mirror actually moves when you're moving the index arm. Then you want to start to bring the entire instrument down, aiming it towards the horizon. At the same time, you want to use that clamp to move the index arm and keep the celestial body in the center of the horizon mirror. Once you reach the horizon, you want that to be in the middle as well. For the final part, you bring the celestial body to the center of the image. You'll normally find there's a little optical quirk here that means you can see both the horizon and the body if you have it right in the center. That doesn't work in my example as this is all computer generated. Once you've got it as close as possible with the clamp, you can then use the micrometer to do the final fine adjustment to bring the body in line with the horizon. At this point, if you use the shades, you might find that you need to remove one of the horizon shades to make the horizon easier to see. Just be certain you're removing the correct shade, otherwise a bright body could burn your eyes. With a star, it's easy to line up a tiny dot of light, but with a large body like the sun, or our red sphere here, it can be a lot harder. Almanacs usually give an upper limb and a lower limb measurement, so you can line up the top and the bottom respectively. In this case, I've aligned the lower limb with the horizon. When you think it's all lined up, you should slowly rock the sextant from side to side, keeping it pointed straight ahead. The celestial body will appear to follow a path in the image. All you're doing is checking the sextant was perfectly upright when you took the sight. If it was upright, the body will just kiss the horizon at the lowest point on its rocking path. If it wasn't upright, the body would drop slightly below the horizon. If this happens, you just need to use the vernier again to make the lowest point on the path just kiss the horizon. Now you've got the sight properly set in the sextant, and you can just read off the measurement from the scale arc and the vernier. Any index error then needs to be applied to get the correct reading. For example, say you measure a body's altitude at 12 degrees 25.2 minutes, and you have an index error of 1.5 minutes off the arc. You need to add those 1.5 minutes to your measurement. Your altitude then becomes 12 degrees 26.7 minutes. Likewise, if your error was on the arc instead, you would just subtract it from your measured altitude. And now that brings us to the end of this Sextant tutorial series. Hopefully you found all the information useful and are now able to take sights using your own sextant. If you have any questions or suggestions for further tutorials, just let me know in the comments below. Otherwise, until next time, thank you for watching and goodbye.
Okay guys, so this was your tutorial on the principles of sight taking or